Hello, I'm here with another video, this time related to stress versus a strain diagram and properties such as modulus of elasticity, Poisson's ratio, which is denoted by nu, and modulus of rigidity, G. So here we have the elastic portion of a stress versus a strain diagram for an aluminum alloy. The specimen here has a gauge length of 2 inches, so typically the gauge length for a tensile test is 2 inches, diameter of 1/2 inch, and this is usually the, as I said, the size for a threaded sample that is used for a typical tensile test. So here, if you put this under the action of a load that is 10 kip, 10 kip means 10,000 pounds, right? As a result, as this guy extends in the axial direction, and this is the axial direction, right? So this is the axial direction. It will actually shrink, or the diameter will get reduced to a new value of 0.49945. So the 0.5 decreases to that. And we want to calculate the following properties, such as modulus of elasticity, Poisson's ratio, and modulus of rigidity. But look, modulus of elasticity, actually, all you have to do is to figure out the slope of the linear elastic zone. So slope is rise over run. So if you take 70 KSI, which means 70,000 PSI, and divide by 0.00614, which is dimensionless, that should give us the modulus of elasticity of about 11,400.65, which is KSI. So that's the modulus of elasticity. Let me rewrite it here for you, 11,400.65 KSI. So here we go. That was easy enough. Okay. So now, how do we find Poisson's ratio? Let's see what is the definition of Poisson's ratio. Poisson's ratio is defined as the negative of the ratio of lateral strain to axial strain. And we have to define what is axial and what is lateral. Kind of, I showed you what the axial direction is. Axial direction is actually the direction that the load is applied. Here the load is applied in this direction. So this becomes axial direction. And then the direction perpendicular to that, be it like that, or coming out of the board like that, would be the lateral directions. So the red is lateral. So lateral actually here is the direction of the diameter. And if we go ahead and use the definition of epsilon, which is change in whatever, in this case change in diameter over diameter, that would be actually the lateral strain. So the lateral strain would be, as I said, change in diameter. So if you have 0.49945, that's the final diameter minus initial diameter divided by initial diameter, that lateral strain comes out to be negative 0.0011 and dimensionless. So the reason it's a negative epsilon is because the final diameter is smaller than initial diameter. Okay. How do we find now, so we got lateral strain, how do we find axial strain? To do that, we're going to first find the axial stress, which is load divided by area. If you take the 10 kip load and divide it by cross-sectional area, the initial cross-sectional area, which is pi over 4 diameter squared, the result's going to come out in KSI. That should be about 50.93 KSI. So basically, what we are trying to find out is at this value of about 51 KSI, 50.93 KSI, 50.93 KSI, what is the epsilon? That's the epsilon axial. Typical mistake is that some people take this number by mistake. That is actually epsilon at this value of 70 KSI stress. So how do we do that? Very easily. How do we find epsilon axial? We use Hooke's law, sigma equal E epsilon, which is actually coming from here, from this equation. E is sigma divided by E. It's sigma divided by epsilon, rather, sorry. So here, epsilon axial becomes sigma axial, which we already calculated, divided by E. So if I take 50.93 KSI and divide it by the E that I calculated at the beginning, 11,400.65 KSI, the result again is a dimensionless value of 0.00 0.004467, which is the epsilon axial. So now we are ready to calculate Poisson's ratio, negative of the lateral strain over the axial strain. Lateral is negative 0.0011 divided by 0.004467. The reason, by the way, we have this negative here is to avoid getting an answer which is negative for nu. Nu is just a ratio, and we want it to be positive. 0.246 would be the Poisson's ratio for this alloy. And keep in mind that actually Poisson's ratio for any known materials cannot be larger than 0.5. So nu should be between 0, larger than 0 obviously, and less than or equal at most 0.5. Okay, last thing we have to find is G. Now, there is a relation between G, E, and nu. It turns out that if you happen E and nu, the formula that you use is G is equal to E divided by 2 times 1 plus nu. So if you use that equation, take 11,400.65 and divide it by 2 times 1 plus 0.246 that I just calculated for you for Poisson's ratio. This comes out to be about 4,574.9 KSI, and that would be the modulus of rigidity. I hope you liked this video. Hopefully I'll come up with some new videos on different topics, different concepts. Again, thanks for watching and listening.